Welcome to Lecture 11 of Physics 506. In this lecture, we're going to be discussing a Cartesian factorization method for solving hydrogen that solves for the hydrogen wave functions without using angular momentum. And I just want to point out that the factorization, this Cartesian factorization, was discovered only in 1984, and I've actually been the person who figured out how you can construct a wave function from this, and we haven't actually even finished the paper and published it yet. So you're getting stuff that's really new things that we're going to be looking at in the work that we're talking about today. I also want to apologize at the beginning. This is going to be a long lecture, and this lecture is going to be very technical because there's a lot of technical details, a lot of algebra you have to go through in order to make this work. You also are going to be introduced to a number of things that I believe you're going to be seeing that are new to you, and it's going to take a little bit of getting used to these new things to feel comfortable with them. Why are we doing it this way? Well, it turns out this is the easiest way to get at the wave functions of hydrogen in momentum space. And the wave functions of hydrogen in momentum space are very important because they can actually be measured in an experiment. And I'm going to be talking about that at the end of the lecture. All right, so let's go ahead and jump in and get started. We're going to be working with what are things that are called harmonic polynomials. These are homogeneous polynomials in Rx, Ry, Rz. Homogeneous means that every term in the polynomial has the same power if I count powers of Rx, Ry, and Rz and add them all together. There's a total of L powers of Rx, Ry, and Rz in a particular homogeneous polynomial. In particular, except for the homogeneous polynomial of degree 0, no homogeneous polynomials have constant terms. And they also solve Laplace's equation. So del squared acting on a harmonic polynomial is equal to 0. Those are the two defining relations of the harmonic polynomials. What we want to do is we want to re-express those in terms of operators. So the way that we do that is, interestingly, if I take the commutator of the polynomial with the radial momentum, it's going to act like differentiating with respect to r, and it's going to remove a power of r from the polynomial. And then if I multiply by r hat, I bring that power of r back. So it ends up actually counting each power of r that I have in the polynomial. It's, of course, multiplied by a minus I h bar. But you see from that first commutation relation that it becomes minus I h bar L times the original polynomial. And when that holds so that is equal to that L, then it is a homogeneous polynomial of degree L in those variables Rx, Ry, Rz. And the second one uses a nested commutator where the alphas are the same. If you think carefully about that, if you rewrite the momentum operator as minus I h bar d by d r alpha, you will see that that actually corresponds to a sum, because I'm summing over alpha, of the second derivatives of that harmonic polynomial with respect to x, with respect to y, and with respect to z. And setting that equal to 0 means that it solves Laplace's equation. All right, so examples of harmonic polynomials are a constant 1, Rx, Ry, Rz. Those are the first order ones. L equals 2 are Rx squared minus Ry squared, Rx, Ry, Ry, Rz, Rz, Rx, and Rx squared plus Ry squared minus 2 Rz squared. Let's take a look at Rx, Ry. Obviously, that's a order 2 polynomial, so it satisfies the homogeneous polynomial part. If I take a second derivative with respect to x, it's 0. If I take a second derivative with respect to y, it's 0. If I take a second derivative with respect to z, it's 0. So it satisfies Laplace's equation. And by calculating these derivatives, you can verify all of these guys satisfy Laplace's equation, and they're all homogeneous polynomials in each grouping. They correspond. The 1 is the S waves, the Rx, Ry, Rz are the P waves, and the quadratic ones are the D waves. They correspond to those terms in spherical harmonics, but it's the Cartesian form of the spherical harmonics. So these polynomials have definite L but they, in general, are not eigenvectors of LZ. In addition, if you write down the harmonic polynomial divided by r to the L, you will find that that harmonic polynomial is just a function of cosine theta hat, sine theta hat, cosine phi hat, and sine phi hat. All right, so this Cartesian factorization was discovered by Yaffe and co-workers in 1984. And what it says, let's just remind you of what the hydrogen Hamiltonian is. It's the sum over alpha p alpha squared over 2 mu, mu being the reduced mass, minus e squared over r hat. And I'm generalizing it and calling it h of lambda, introducing a lambda in the denominator. We care about the case where lambda equals 1, but you'll see why we're working with a general lambda as we go further in the work that we're doing. We want to rewrite that as a sum over alpha of a dagger alpha of lambda times an a alpha of lambda plus some e tilde of lambda, where each of those a's are these Schrodinger-like raising and lowering operators for each Cartesian coordinate, x, y, and z. And I'm telling you exactly what they are for this solution. It's 1 over square root of 2 mu, p alpha minus I h bar over lambda a0, r alpha over r hat. Now, we have to go through and we have to do the calculations. So a dagger alpha of lambda, a alpha of lambda is 1 over 2 mu. I'm going to get a p alpha squared. I'm going to get minus I h bar over lambda a naught, the commutator of p alpha with r alpha over r hat. And then I'm going to get plus the square of that term, plus h bar squared over lambda squared a0 squared, r alpha squared over r squared. Now, we have to go ahead and work out those commutators. The commutator of p alpha with r alpha over r hat, that's going to equal minus I h bar over r hat. I'm using Leibniz, so I'm going to have one term that's a commutator of p alpha with r alpha, and I'll have one term that's a commutator of p alpha with 1 over r hat. It'll be plus I h bar r alpha squared over r hat cubed. You can work that out using the same kinds of relationships that we have worked out when we're working with commutators of momentum with the radial functions. I believe you might have even worked that out on a homework exercise. And now we just substitute that in. And what we get is a alpha dagger of lambda, a alpha of lambda is p alpha squared over 2 mu minus h bar squared over 2 mu a0 lambda 1 over r hat. That we're getting from the first term in that commutator, plus h bar squared over 2 mu lambda a naught r alpha squared over r hat cubed, plus h bar squared over 2 mu lambda squared a0 squared r alpha squared over r hat squared. Now, we need to sum this over alpha, but I want you to remember that the sum over alpha of r alpha squared is r squared. That's going to be very important in what we're doing. In fact, you see it's going to be converting things that are operators into constants, and that's how we make this Cartesian factorization work. So let's sum over alpha. We're going to get a px squared over 2 mu, a py squared over 2 mu, and a pz squared over 2 mu. I'm going to get minus 3 h bar squared over 2 mu a0 lambda 1 over r hat. I'm going to get plus h bar squared over 2 mu a0 lambda 1 over r hat, because that sum over alpha of that r hat alpha squared is just going to give me r squared. That's going to cancel 2 factors of r hat in the denominator. And then we're going to get plus h bar squared over 2 mu lambda squared a0 squared, because the r squared in the numerator cancels with the r squared in the denominator. Now we're going to use the fact that h bar squared over mu a0 is equal to e squared. And substituting that in, we're going to get px squared. We're going to get the kinetic energy the same as it was, minus e squared over lambda r hat, plus e squared over 2a0 lambda squared. That tells me that my e tilde is minus e squared over 2a0 lambda squared. And indeed, this then is a factorization. We've established that h hat of lambda is a sum over alpha, a dagger alpha of lambda, a alpha of lambda plus e tilde lambda. Okay? Now, that means the ground state satisfies each of these a alphas acting with lambda equals 1, acting on the ground state is equal to 0, where alpha runs over x, y, and z. That means that p alpha acting on this state is equal to I h bar over a0, r alpha over r acting on this state. The ground state energy is equal to minus e squared over 2a0. And of course, that's correct. We know that that's correct. you can actually integrate those differential equations that you get by rewriting the P alpha as minus I h bar d by d r alpha, and use that to solve for the wave function. But we're going to be working on it a slightly different way. We're going to be using that relationship between the P alpha and the R alpha over R hat in a lot of the work that we're going to be doing. Okay? All right. So I'm just reminding you here that there's a lot of technical details. Some of the technical details are going to be given to you to put into the homework. Other ones I'm going to just skip over because it really is quite technical. Now we start by defining the perpendicular kinetic energy by taking that total Cartesian kinetic energy and writing it as 1 over 2 mu pr squared plus t perpendicular. Now you know from separation of variables that t perpendicular is really the angular contribution to the kinetic energy. But remember, we're not really working in angles here. We're working with Cartesian coordinates. So we're going to just write it as 1 over 2 mu, the sum over the Cartesians minus a pr squared. And a critical identity that you're going to show on the homework is that when that t perpendicular acts on a harmonic polynomial and acts on a state phi lambda that I'm going to define for you, what you get is h bar squared L times L plus 1 over 2 mu r hat squared times that harmonic polynomial acting on the state phi lambda. Phi lambda is the ground state of h of lambda. We just worked out what phi 1 is, but we can work out phi lambda for arbitrary lambda. The equations are slightly modified in those cases. What that then tells us is that t perpendicular minus h bar squared L times L plus 1 over 2 mu r squared annihilates this harmonic polynomial acting on this state, which means that the harmonic polynomial acting on that state has total angular momentum L. In essence, it's an eigenstate of the total angular momentum with eigenvalue, or with quantum number L. And you get that if you just recognize that t perpendicular is L squared over 2 mu r squared from our previous work. Okay. Now, the intertwining relationship is much more complicated, and we're going to just sketch it for you here. We start by looking at commutation relations. So we're going to be working with those same BR of lambda. I'm going to now introduce a lambda in there as the general BR. 1 over square root of 2 mu PR minus I h bar 1 over A0 lambda minus lambda over R hat. I'm going to have a B dagger R of lambda, BR of lambda plus E tilde of lambda. That, if I just go ahead and calculate that, you find that that's going to equal PR squared over 2 mu plus H bar squared lambda times lambda plus 1 over 2 mu R squared minus E squared over R hat. That's essentially what we did in the last lecture, but we were using lambda equals L in the last lecture. You can also calculate them in the opposite order, adding an E tilde lambda plus 1, and you find that that's equal to PR squared, H bar squared, lambda, lambda plus 1 over 2 mu R squared minus E squared over R hat. I do want to point out that here, the E squared is E squared over R hat, not E squared over lambda R hat. Okay? And what that tells us is that H of lambda equals 1 can be written in many different ways. We can write it as BR dagger BR plus T perpendicular minus this term H bar squared lambda lambda plus 1 over 2 mu R squared plus a constant. And similarly in terms of a BB dagger. Now, to set up the intertwining, what we're going to do is we're going to calculate the commutator of T perpendicular minus H bar squared L times L plus 1 over 2 mu R squared with the B dagger R of lambda. And if you substitute in what the BR is, now the BR only has one term that isn't going to commute with that. That term is going to be the term that is the PR term. And then, of course, the T perpendicular, we have to check to see whether or not that commutes with the R-dependent terms in the B dagger R of lambda. So let's go ahead. I'm telling you what the answer is, but let's go ahead and actually compute it. So we write out the PR plus IH bar 1 over lambda A0 minus lambda over R hat. We're going to substitute in the T perpendicular is L squared over 2 mu R hat squared. That allows us to just calculate the commutator. Now, PR commutes with L squared, but it doesn't commute with 1 over R hat squared. So we have that commutator we have to work out. And then we have a commutator of the 1 over R squared term from that H bar squared L times L plus 1 over 2 mu R squared with the PR. The L squared commutes with R hat and it commutes with constants. So those other terms we don't have to worry about. Now when we go ahead and evaluate those commutators and we collect our terms, we find we get minus 2I h bar over square root of 2 mu r hat t perpendicular minus h bar squared L times L plus 1 over 2 mu r squared. Now, the trick is what we do then is we actually write out that commutator in the upper part of the page as t perpendicular minus that other term times b dagger r minus b dagger r times that t perpendicular. And then what we're going to do is we're going to bring the b dagger term times that t perpendicular over to the left-hand side. And you see now I can factor out the t perpendicular minus h bar squared L times L plus 1 over 2 mu r squared. And I find what happens is when the b dagger moves through that term, it shifts the b dagger by minus 2I h bar over square root of 2 mu r hat. So now that looks like an intertwining relationship. We can move the t perpendicular minus h bar squared L times L plus 1 through this b dagger r by shifting the b dagger r. Okay. Now, what we're going to show is if we take that same product of string of b operators, multiplying this r hat n minus L minus 1 phl of rx, ry, rz times our ground state with lambda equals to an integer n. It has to be an integer, and we're going to see why it has to be an integer in a moment. You can work out an intertwining relationship, and you're going to do this on the homework. The intertwining relationship is more complicated. So when the h moves through that string, it's going to pick up a bunch of shift terms. And the shift terms differ as it moves through each one of those b operators. And I have to add all of them up. So I'll get the h of lambda equals 1 plus h bar squared over mu r squared sum j equals 1 to n minus L minus 1 of n minus j. So that is similar to the standard intertwining relationship. But I get a whole bunch of extra terms as well. I get a product of the b dagger terms that have been shifted, subtracted by a product of the b dagger terms, and the whole thing multiplied by t perpendicular minus h bar squared L times L plus 1 over 2 mu r squared. Now, to show that that ansatz that we predicted was an eigenstate, we recall that that t perpendicular operator, when it acts on this harmonic polynomial times that r hat to the n minus L minus 1, it gives 0. So that extra piece that we got from the intertwining, that goes away when we operate it on the state. So we're just left with something that looks more like our normal intertwining. We still got to move through that r hat to the n minus L minus 1, and we have to move through the harmonic polynomial. But it turns out we can move p hat to the L over r hat to the L to the left because that guy depends only on angles and it commutes with PR. So after we can get rid of the t perpendicular, we can move that term through the PR. We also can do this summation, sum j equals 0 to n minus L minus 1 of n minus j. You guys should know what the sum over integers are. The sum over the minus j, I'm going to get n times n minus L minus 1 minus 1/2 n minus L times n minus L minus 1. And when you look at that, when you evaluate that, you get n minus L minus 1 times n plus L times 1/2. That's because, so you can see that there's an n minus L minus 1 term that factors out, and you're left with a 1/2 n plus L after doing that. And then you can just multiply that out, and you find you get n squared minus n minus L times L plus 1, the whole thing times 1/2. Okay, now let's take a look at what the h is. The h acting on this state is going to equal this pH times this rx, ry, rz, over r hat to the L times a pr squared over 2 mu minus e squared over r plus h bar squared over mu r squared n times n minus 1, whole thing acting on r hat to the n minus 1 because that's the only term that is left. So now, and again, we want to, I actually skipped something, so let me start that over again. We write h of lambda equals 1 as plus this h bar squared times that summation. That is equal to pr squared over 2 mu plus t perpendicular minus h bar squared over mu r squared L times L plus 1 minus e squared over r hat squared plus h bar squared over mu r squared times n minus 1. You see I borrowed that minus L times L plus 1 over 2 mu r squared, and I am associating that with a t perpendicular, and then that thing annihilates against the PHL of Rx, Ry, Rz. So that term disappears, and then I'm left with the PR squared over 2 mu minus E squared over R hat plus H bar squared over mu R squared N times N minus 1. I can then take my PHL, that harmonic polynomial, divided by R to the L. That becomes an object that just depends on angles. It commutes with the PR squared, so I can move it to the left of the PR squared. So I'm left just with this R hat to the N minus 1. And now we have to calculate commutators. I have to calculate the commutator PR squared with R hat to the N minus 1. And this requires some algebra. I'll let you carefully sit and go through that algebra. You might even want to pause the video here, and then I'll reveal for you what the final answer is. It's at the bottom of the page there. And we can then substitute that in and move that PR squared through that R hat to the N minus 1, and we have this big expression that is left, PR squared over 2 mu minus E squared over R hat minus IH bar N minus 1 over mu 1 over R hat PR plus H bar squared over 2 mu R squared N times N minus 1 minus N minus 1 times N minus 2. You see there's a common factor of N minus 1. I can pull that out. I'm left with just 2 times N minus 1. You also can see that the term 1 over R hat PR, because the PR acting on the phi N is equal to 1 over NA0 minus 1 over R hat times an IH bar. I can substitute that in, and then I can repeat that. And so, well, first what I'm going to do is do some simplifications. What you find is you're going to get two terms that depend on N minus 1 that cancel, one with a minus sign, one with a plus sign. And we're going to still have a term left over, minus H bar squared over mu A0 N minus 1 over N times 1 over R hat. We have this PR squared over 2 mu minus E squared over R hat as well. We have to figure out what happens with the PR squared over 2 mu minus E squared over R. Well, I'm going to associate PR squared over 2 mu minus E squared over N R hat. And that means I have to carefully work through. You see this extra term, minus H bar squared over mu A0, N minus 1 over N, 1 over R hat. H bar squared over mu A0, that's just equal to E squared. And if I add those terms together, the E squared over R terms together, it becomes minus E squared over N R hat. And that is H of lambda equals N. And the state phi N is an eigenstate of H of lambda equals N, and it has an energy En tilde given by minus 1/2 E squared over A0 times divided by N squared. All right. So that becomes a number that gets pulled out. And so what we have established is H acting on this state that we said was an eigenstate is equal to E tilde N times that state. So indeed it is an eigenstate, and the energy eigenvalue is one of the eigenvalues of hydrogen. So indeed we can get the eigenstates and we can show that this works and get the eigenenergies. I also want to point out, we have used the fact that this number N for the phi N, it was indexed by N. I could have written that as lambda, but then I wouldn't have gotten the cancellations with that summation that we got when we used intertwining. We had that sum of N minus J. I really needed that index to be N exactly to cancel those terms in the right way so that you could make this work. And so the quantization is coming about by the fact that I have to make this equal to H of lambda equals N at the end, so I have an eigenstate. If I had any other terms coming out, it would not be an eigenstate of that, and then I would get a complicated expression. So this is where the energy quantization comes in this way of doing the problem using this Cartesian factorization. Okay? Now, just like before, the string of operators, B dagger R of L to B dagger R of N minus 2, they can be replaced by a Laguerre polynomial. I'm not going to do that algebra for you, but I will write down for you what the normalized wave function is. It has a minus I to the N minus L minus 1. It has a NA0 over 2 to the N minus 1. It has a square root of 2N minus 1 factorial, N minus L minus 1 factorial, over N plus L factorial. It has a 1 over R hat to the L, PH L of Rx, Ry, Rz. You can think of that object 1 over R hat times that P. You can sort of think of that like a spherical harmonic. It has a 2 R hat over NA0 raised to the Lth power, L to the 2L plus 1 sub N minus L minus 1 of 2 R hat over NA0 acting on this phi N. Now to get the wave function, we take the overlap with X, Y, Z, and I can just replace those operators, Rx, Ry, Rz by X, Y, Z. I can replace R hat by R, And you can pull all those guys out, and we have just the overlap with the auxiliary Hamiltonian ground state phi n and a bunch of numbers and stuff. I'm not going to read them out for you again, but you should recognize that that looks like some constants, and it looks like a spherical harmonic or spherical harmonic-like object. And I have my Laguerre polynomial, and I have powers of r as well that are coming out from this. Okay? Now, to finally get the wave function, I need to calculate this matrix element, or this wave function, x, y, z, acting on the phi n. And to do that, we're going to work with the translation operator in spherical coordinates. Remember, we derived this in an earlier lecture. And we're going to use that translation operator to go from the origin of the spherical coordinate system, the position eigenstate at the origin, which we're going to just denote bra 0. We have that translation operator, e to the I r over h bar, p hat r plus I h bar over r hat, acting on this state phi n. Now, p hat r acting on phi n is I h bar 1 over na 0 minus 1 over r hat times phi n. That we got from our subsidiary condition, the condition that determined and defined the auxiliary ground state phi n. So what are we going to do? We're going to take that exponential and we're going to expand it in a power series. But first, recognize, take a look at that object, that subsidiary condition. If I take the I h bar over r hat, you see it has a minus sign. I can bring it over to the left-hand side. I get p r hat plus I h bar over r hat acting on phi n. That equals I h bar over na 0 times phi n. That's an eigenstate eigenvector relationship, because I h bar over na 0, that's a number. It tells me that the state phi n is an eigenvector of the operator pr plus I h bar over r hat. Well, lo and behold, that's the operator in the exponent. So I can just replace that operator by its eigenvalue, which is I h bar over na 0. And you see what we find is it's equal to e to the minus r over na 0. And I forgot to put in there should be a 0 phi n. There's a normalization constant that we get as well that's left over. Okay, that's our position space wave function. We needed that exponential factor. I told you we were going to get that exponential factor. Here we've done it. You also can do it in the spherical case. It's a little bit different because this has different powers of r associated with it. So the derivation is closely related to this, but it's a little bit different. All right, but as I told you at the beginning of the lecture, what we really wanted to do is we wanted to calculate the momentum space wave function. So we want to look at the overlap with a px, py, pz. And now things get hard because px, py, pz is not an eigenstate of pr. Remember, we told you pr was not a self-adjoint operator. It doesn't have normal eigenstates. And remember, pr involves momentum and position in it, so it's a complicated operator. So now doing this full calculation is technical and it is complicated. But instead, what we're going to do is we're going to first just look at the ground state, n equals 1, L equals 0. In that case, the harmonic polynomial is just equal to 1, so I can get rid of it. And psi 1, 0 of px, py, pz is the overlap of px, py, pz with psi 1. Psi 1, again, being defined by its subsidiary condition that the ax of lambda equals 1 acting on psi 1 is equal to 0, and so is the ay and the az. So now we can use just the Cartesian translation operator for the momentum in terms of the rx, ry, rz operators and translate that state from the origin in momentum space. That's the p equals 0 ground state, which is a delta function in momentum space, or if you like, it's just a constant because it's a plane wave with k equals 0. And we're going to now expand that exponential in a power series. So I now have to calculate this operator, origin of momentum space bra, px, which is a number, rx operator, plus py number, ry operator, plus pz number, rz operator, raised to the nth power. And then I have the Coulomb ground state, psi 1. Let's take a look at the case n equals 1. Remember, p hat alpha psi 1 equals I h bar over a0 r hat alpha over r hat psi 1. I'm going to multiply that by an r hat on both sides, and then I'm also going to multiply it by an a0 over I h bar. You see, I can replace the r hat acting on psi 1 by a p hat acting on psi 1 times some numbers. So I'm going to get this to equal a0 over IH bar, bra origin of momentum, r hat, px number, px operator, plus py number, py operator, plus pz number, pz operator times psi 1. I would like to just operate that px on the origin and set it equal to 0, but I got to move through the r hat first. So I have to do the commutator. I have to add in the commutator of r hat with px, py, and pz. So we can go ahead and do that when we have to remember that that commutator is equal to r alpha over r hat times IH bar. So we're going to do that. I'm going to just write it as a sum over alpha. The other term, once I've added in that commutator, then I have the r hat to the right of the p hat operators. Then the p hat operators annihilate against the origin in momentum space. So those terms go away, and I don't have to worry about them, which is why I'm only left with the commutators. Now, the commutator gave me a term that went like r alpha over r hat. But r alpha over r hat is proportional to p alpha. And when p alpha acts against the bra, it gives 0. So then the whole thing is equal to 0. When I raise it to the first power and I look at that expectation value, it's equal to 0. In fact, we're going to find all odd powers vanish and are equal to 0. Now, for the general case, we have to consider this raised to the nth power. And we're going to just expand this out. I'm going to look at it as a product of pxrx plus pyry plus pzrz times pxrx plus pyry plus pzrz. I'm going to write out all of those terms as a sum over alpha 1, alpha 2 out to alpha m of p alpha 1, r alpha 1, p alpha 2, r alpha 2, etc. You should be able to verify that that expression that I've written for you there is a correct expression. Now I have to take the expectation value. The p alphas are all numbers. I can pull those all out. I have this expectation value of the product of the r alphas. We're going to replace r alpha to the m by a0 over IH bar r hat p alpha. And I am then going to write it. I can re-express that as a commutator with the p alpha, because when p alpha hits that bra, it gives 0. But it's now a commutator with the entire expression, r alpha 1 out to r alpha m minus 1 times r hat. Now that commutator is going to act on each of the r alpha j's, but it's going to be 0 unless alpha j equals alpha m. And when it is equal to alpha m, it's going to just give IH bar. And that means I'm going to get the same result for every alpha j from j equals 1 to j equals m minus 1. And then when it hits the r, the commutator is IH bar r alpha over r hat. So that alpha is going to be an alpha m because it's p hat alpha m that's doing the commutation. So you have to now go through a careful counting exercise. You're going to get a0 times a p squared, because I'm going to have a delta function that sets one of those alpha j's equal to an alpha m, and I'm going to sum over the alpha j. That's going to give me a p squared. I'm going to have a sum over alpha 1 out to alpha m minus 2 because I lost the alpha j summation. I'm going to just relabel all my alphas so that they run from alpha 1 to alpha m minus 2. I get m minus 1 copies of this because the alpha j, the j could equal 1 all the way out to m minus 1. And I then have this expectation value of the momentum bra, r alpha 1, out to r alpha m minus 2 times r hat. And you can see that's the same as what I had before, but I removed one of those factors of r alpha m minus 2. Now, when I have the commutator with the r hat, that gives me an r alpha m. So I still have the summation of alpha 1 all the way out to alpha m. I have an a0 out in front, and I have a 1 over r hat. Okay? Now, in the first term, we're going to take that r and we're going to rewrite it as the sum of an alpha m minus 1 of r alpha m minus 1 squared divided by r hat. Okay? Because when I sum over alpha m minus 1, sum of r alpha is rx squared plus ry squared plus rz squared. That's equal to r hat, and I'm dividing by r hat. So that is then written as the sum alpha m minus 1, r alpha m minus 1, r alpha m minus 1 over r hat. Now, again, we know what r alpha m minus 1 over r hat is when it acts on the state psi alpha. So I can replace that r alpha m minus 1 over r hat by a p alpha m minus 1. And I will now get a commutator again because it annihilates against the bra. So those first terms, those m minus 1 terms, I'm going to get another commutator here with a p alpha. But notice here there's no r hats in it. It's just the r hat alphas that are in that. And then with the second term, because it's a 1 over r hat, I'm going to associate the r alpha m over r hat, and I'm going to get a p alpha m for that one as well. And again, that's a commutator just with the r alphas. All right. Now again, it's a careful counting exercise. Every time that p alpha hits one of the r alphas, I'm going to get a delta alpha m minus 1 alpha j. And I have to count how many of them I have. And I'm going to get a p squared that comes out of that because they're going to be pinching together. So we're going to get this a0 squared p squared m minus 1. I'm going to get m minus 2 plus 3 of these objects. I'll have a sum alpha 1 out to alpha m minus 2 of the r alpha out to r alpha m minus 2, multiplying the psi. And then when I look at the second term, I'm going to get an a0 squared and m minus 1 times p squared. M minus 1 is from all the different terms that I have. And I get the summation out to alpha m minus 2. I get all the p alphas that are multiplying it, and I get the string of r alphas out to r alpha m minus 2. You can see those matrix elements now are the same. So I can combine these terms together. And let's just look again at that top line again to make sure we have the counting right. The alpha j's, there are m minus 2 alpha j's where alpha is not equal to alpha m minus 1. The p alpha m minus 1 with the r alpha m minus 1, there actually are 3 of those that contribute. So we get m minus 2 plus 3. That's where that comes from. And we get m minus 1 in the lower one because there are j terms. None of them are equal to alpha m, so they're just j different terms. Each one is going to give us the same result for that. And you can see now that because these are equal, I'm going to get an extra one that I'm adding. So that m minus 2 plus 3 is equal to m plus 1. But I'm going to get an extra one from that last term. It's going to become m plus 2. And now you see what has happened is we've taken this expectation value of the sum over alpha, p alpha r hat alpha raised to the nth power. We've gotten some numbers in front times the expectation value with an m minus 2. So this is ready to be iterated. Again, the odd ones vanish because eventually we're going to hit m equals 0 or m equals 1. And we verified that the m equals 1 expectation value is equal to 0. So we're going to call this expectation value for m, we're going to call that mu m. And the recurrence relation we found is mu m is equal to m minus 1 times m plus 2 times a0 p squared times mu m minus 2. And then we just iterate this all the way down to the end, and you get an m factorial. You get an m over 2 plus 1, a0p to the mth power times the expectation, the overlap of 0p with psi 1. So this means we've now calculated for all the even powers. Again, odd powers all vanish. So we substitute in just for the even powers. I have to make that summation of the exponential to only involve the even terms. You look at all of the different terms. You see there are cancellations of the 2n factorials. The minus I squared becomes minus 1. These h bars can be collected with the a0p's. I get a0p over h bar to the 2n power. I have an n plus 1 left over. And then I have the overlap, this 0p with the psi 1. Okay? Now, this term looks like sum over powers with a minus 1 to the n. It looks very much like a geometric series. You should recall the geometric series. 1 over 1 plus z is the sum n equals 0 to infinity minus 1 to the n, z to the n. If you have not seen this before, I do recommend you go and search the web. I'm sure there's a Khan Academy video on geometric series that you can go look up and see how you work with the geometric series. It's really a relatively simple thing to do, but it's really worthwhile that you work it through and figure that out for yourself, how that works. Now, what happens if I take a derivative of that geometric series? If I take a derivative of the geometric series, I'll get minus 1 over 1 plus z quantity squared on the left-hand side. On the right-hand side, I pull down a factor of n times the z to the n minus 1. I can drop the term with n equals 0 because there's an n coefficient. So that summation goes from n equals 1 to infinity. And then I let n go to n plus 1, and I'm going to pull out a minus sign from the minus 1 to the n. The n will go to n plus 1, and I'll get the n minus 1 in the exponent goes to an n. I'll get z to the n. And lo and behold, that's the summation that we have. So that term is just equal to minus 1 over 1 plus z quantity squared. Or it's equal to plus 1 over 1 plus z quantity squared. So we're going to plug in that 1 over 1 plus z. Z is equal to a0p over h bar. So we plug that in, and then we have this normalization constant. To get the normalization constant, I take the square of that thing and integrate it, and the normalization constant comes out to be square root of 8 over pi. Okay? Now, you might ask, look, this was hard, really torturous. Why did you make me go through this? Well, first off, I think the fact that we can find a Cartesian factorization of hydrogen is cool. The fact that we can solve for hydrogen without introducing spherical harmonics is cool. But the really important thing is we wanted to get to this momentum space eigenstate, because the momentum space eigenstate can actually be measured. There's this procedure called E2E spectroscopy. What you're doing is you're scattering an electron off of hydrogen, and the scattering amplitude is proportional to the square, the modulus squared of the momentum space wave function of hydrogen. Take a look at that momentum space wave function. The probability, the square of that is something that kind of looks like a Lorentzian. It's a maximum at p equals 0, and it decays in some smooth way as you come down from 0. And what I've sketched for you is what the actual curve is in the solid line, and the x's are the experimental data from an experiment that was done for this. And, it essentially lies on the curve. So you might ask the question, as most quantum mechanics students do, what does the hydrogen wave function really look like? What does an atom really look like? Okay? And normally the answer to that is, we don't really know. You could say something about, well, there's a probability distribution in momentum space, and if I did a measurement of the electron in position space, I would get that distribution. But the reality is no one knows how to do that measurement in position space. It cannot be done, or no one has been sharp enough to figure out how it can be done. The only thing that has been done is that experiment has been done in the situation where the hydrogen atom is in an electric field, and then there's a magnification effect, and you can actually get the wave functions of a hydrogen atom in a strong electric field. I think it said magnetic field. I meant electric field. In a strong electric field. But that's not the same as the wave functions in the absence of an electric field, because the electric field changes the wave functions of the hydrogen atom. This E2E spectroscopy actually measures the square of the wave function in momentum space. So this is how we can image an atom. So we have to take a look at what is the momentum space wave function to understand how to visualize an atom in an actual experiment. Now, why do we only care about the 1s state when we do this? Well, you need a lot of atoms in order to make this work. And excited states of hydrogen don't stay in the excited state for very long. So if I do the scattering experiment, even if I'm bombarding my hydrogen gas with lasers to get them into an excited state, most of them are still going to be in the ground state during the time of this scattering. And that means I'm going to be getting the wave function corresponding to the 1s state. So it's really only meaningful to do this calculation for the 1s state. But this measurement has actually been used to calculate and view the wave function in momentum space for a number of different atoms. They like to look at the noble atoms a lot, the helium and xenon and neon and so forth. They like to look at molecules. They've even done this in solids. It turns out for solids, there's a much better experiment that is much more accurate called angle-resolved photoemission spectroscopy, which is essentially the photoelectric effect on steroids, and that's what Einstein won his Nobel Prize for. That experiment has sort of superseded this. So this experiment isn't really done very much anymore. There might be some diehard practitioners of it who are doing it for some things related to molecules, but it's not really used very much anymore. But it still is the only direct way that we can image the hydrogen atom. And what I drew for you on the page here is what that image is. Okay, apologies for the fact that this lecture is long. That's mainly because it had a number of technical parts to it, but I think it's worth it because there were a lot of really interesting things that we managed to do with the results of the calculations. And it's just a different way of looking at the hydrogen atom, and I'm sure none of you have seen it before because it's not available to the general public anywhere else except in this class. All right, so that ends this lecture. In our next lecture, we're moving on to looking at angular momentum and how you combine angular momentum and add angular momentum. And then after that, we're going to be moving on to perturbation theory. So with that, I'm going to end the lecture.